I'm going to start by giving you the world's fastest and quickest lesson in risk assessment. Okay? It says that risk assessment requires both the probability and the consequence of a given hazard to be assessed. That's the end of the lesson on risk assessment. Any questions? Okay. Basically, if we only cared about the consequence axis of risk assessment, we would never cross the road. We would all be living in some sort of asteroid shelter because that's the worst possible consequence. Obviously, when we're assessing a risk, we assess not just how bad the potential consequence is, but also the probability of those consequences happening. Okay, so this is just a mock-up of a risk assessment matrix. Many of you perhaps familiar with these sorts of matrices. So we've got a probability axis and we've got a consequence axis. Okay, so we're going to look at the sorts of climate impacts that might populate this consequence axis, and then we're going to look at the probabilities. Now, the issue that we come to when we start looking, if we're interested in adaptation, so if we're interested in how high do we have to build the dam wall, or the levee wall, or whatever it is that we're trying to do to avoid the impact, we run into the problem that we have this uncertainty. Okay? Now, anyone who's been paying attention to climate change knows about uncertainty. All right? Where does it come from? I'll argue that a lot of that uncertainty stems from the emissions that are driving the projected impacts. Okay? So we've got a range of emission scenarios. I'll go into this in a little bit more detail. Within each scenario, you then model, or the climate models rather, model the future climate, and there's a whole lot of uncertainty that comes from the climate models. Okay? And then we've got an overall uncertainty of our climate projections. This is a gross simplification of the climate modelling process, obviously, but that's roughly the way it works. Okay, so if we take that overall uncertainty, that is now on our consequence axis of our risk assessment. So we've got, now this is another gross simplification. I'm saying that the more severe climate change impacts are basically to do with the high emission scenarios, and the less severe climate change impacts are associated with the low emission scenarios. Hopefully that's not overly controversial. I know that it is a simplification and it doesn't hold in all cases, but let's just carry that through. All right. The question then is, what about this probability axis? Okay, we've seen all sorts of graphs already this morning that show, in fact even in the previous presentation, show very severe and potentially catastrophic things happening under the high emissions case. Are those likely? Are they very likely? Are they only hypothetical? Let's look at the two scenarios that are mainly used in the projections for South Australia at least. RCP8.5 is the red one. RCP4.5 is what's being called the intermediate scenario. Okay? I want to just draw your attention to a couple of things. I just pulled this figure out of the Climate Ready document. Okay? One thing is I'm just going to have a quick, just for fun, look at that intermediate word. The other thing is that we've got this statement being made, greenhouse gases are tracking at or above the RCP8.5 trajectory. Okay? Many of you will be familiar with statements like that. So first of all, let's just have a look at this intermediate. What I'm looking at here is the old emission scenarios. If you've been dealing with climate change for more than the last couple of years, you might remember the SRES scenarios, and basically we had a high, medium and low. Now, if we replace the background image with the new emissions scenarios, which are called the RCPs, the representative concentration pathways, these came out in 2011, they replaced the SRES scenarios. There's a widening of the overall scenarios. There is now a lower low scenario and a higher high scenario. That thing there is the old, what we call the low scenario. And this is what we're now calling the intermediate scenario. It's almost on the same track as the low scenario. So the point, I'm not trying to sort of draw, make a really profound point about semantics. What I'm saying is if you're dealing with studies of projected impacts that predate the RCPs, you should be looking at the low scenario and comparing that to what we now call intermediate. Anyway, semantics. So, the other thing is, are we tracking above the high scenario? Now, it's embedded in there in the SA Climate Ready document. This is from a few years ago because we were, when we were dealing with the SRES scenarios, the same statements were being made. We were tracking above the A1FI scenario. Anyone remember A1FI? That one? Yeah? Oh, good. So A1FI was the high scenario, if you like. In fact, there were two high scenarios, A2 and A1FI. But anyway, we were tracking above A1FI. That was the point that was being made. And it was true. We were tracking above the A1FI scenario. However, what wasn't said at the same time was that we were, at the time, tracking below the medium scenario. Right? The reason being, if you look at this inset graph here, in fact, the medium scenario was the highest temporarily until about 2030 under that set of projected scenarios. Okay, so all I'm doing in that, the circle that's on here is because this paper was actually talking about the fact that we've reduced emissions for that particular year. We've resumed the growth trend anyway. So I'm just drawing your attention to the fact that tracking on a particular scenario isn't a very good predictor of what might come ahead in the future. All right. Any case. Oh, whoops. So, in any case, I'm not saying that we're not tracking at or above RCP8.5. People who make this statement are implying that there is a higher probability associated with those sorts of impacts, aren't they? Okay, so if we go back to our matrix, basically, we're saying that the high emission scenarios are in the high probability space because that's where we're currently tracking. No sign of reducing our emissions. Therefore, the low impacts must be down in the lower, relatively speaking. Okay? Positions are a little bit arbitrary, completely arbitrary. All right? But I'm going to ask the question, what if we've got that wrong? What if, in fact, we're going to come off that trend and we've actually got a very low probability of achieving these high emissions and a comparatively high probability of getting to the low emissions? That would be helpful when you're faced with a choice between building the levee wall 1 metre high or 3 metres high, depending on the scenario. Okay? So what we're looking for here is a realistic worst case scenario. Not a worst case scenario like an asteroid hitting the Earth where we can't realistically plan for that. We need a realistic worst case scenario. So, defining that scenario, we're going to suppose that there is negligible global action to reduce carbon emissions. I would say that to date, we're probably on track for that scenario. Okay? In that instance then, the emissions are going to depend on the total carbon resource. If we're not doing anything at all about deliberately reducing our emissions, then they will depend on the total carbon fuel resource. And so the question becomes, could we reach this sort of, some of you might have heard of peak oil, peak coal, peak gas, peak fossil fuels? Could we hit that, and then could that limit our emissions in any significant way? Right? There is a whole body of research, whole body of literature dealing with limits to fossil fuel supply. There's a whole other body of literature dealing with climate change projections. And there are about 12 people worldwide who are in the middle trying to bring the two together, and I'm one of them. Okay, so when we come to model the fossil fuel supply, if anyone wants to see the paper, by all means, so I should have mentioned the other author, if you like, of this talk, Steve Moore, is an expert in fossil fuel modelling, has been, got his PhD in 2010, and has been cranking out models of non-renewable resources, not just fossil fuels. Anyway, last year we published a paper that was projecting fossil fuel production per country. So we've divided it into individual countries and individual resources. So we're not just saying all of oil, we're saying conventional oil, shale oil, kerogen, heavy oil, tar sand, etc., and likewise all the different types of gas, including methane hydrates, which aren't even a fuel source yet. Okay, we're trying to create a realistic worst case scenario for the future, and we model it mine by mine, field by field, and what we find is that the trajectory depends on what our assumptions are about how much of that carbon is down there. Okay, we have wildly varying estimates of how much carbon fossil fuels are under the Earth's crust. Even more wildly varying estimates of how much we might realistically get out of the ground, ultimately. Okay, we can't reduce that uncertainty completely, so like any good modelers, we produce scenarios, we put a low, a high, and a best guess, which is somewhere in the middle. Now, without paying too much attention to the numbers, these are in exajoules, which is 10 to the 18 joules. The high scenario ends up with about 2.5 times the energy as the low scenario. The best guess is about a third of the way from the low to the high, based on our estimate of each country's individual resources. That's the ultimately recoverable resource. It's smaller than the known carbon resources that are in place. It's our best estimate, well, our 3 best estimates, if you like, of how much might be extracted. And so then, once we've modelled the world's energy supply, it's very easy to just attach the related emissions factors, and we get a graph which looks like a bowl of spaghetti. So let's just put some, so that's the high scenario from RCP. We have to take it off the chart because it goes so high. There's the low scenario that should really read intermediate, sorry. Now, our models cover this range. So the upper limit of our model, bearing in mind that that is the model that includes all of the methane hydrates and all that sort of stuff, gets us to that area. And then the lower model, which is basically doesn't include methane hydrates, it includes more of a conventional mix, gets us down there. And if we follow the best guess scenario, it gets us somewhere in the middle. Okay? Now that's all past work. That's all published in that Moore et al. Paper from last year. New work that you're the first people to see basically involves taking those emissions and converting them into temperature change. Because I've been banging on about this for a few years, and no one seems to give a rat's about me telling them that our emissions are going to do this and the emission scenarios are going to do that. People want to know what that means in terms of climate change, which is understandable. So now we're going to, what I've done is stochastic analysis, or sorry, what we've done, I should say. Steve Moore did the stochastic fossil fuel projections, varying that ultimately recoverable resource randomly between the upper and lower limits. So we get a spread of different scenarios. We did 10,000 different simulations, fed the resultant emission scenarios for each of those 10,000 simulations into, crikey, right, 2 minutes, into a simplified climate model, which is used widely in these sorts of studies, called Magic C6. That simulates the carbon cycle, how much of those emissions end up in the atmosphere and so on. Put in some non-fossil fuel emissions because you need to include not just CO2. We took those from well, I don't know what we call that one. I suppose it's intermediate to high is RCP6. And basically you then get a spread. Now this is for an equilibrium climate sensitivity of 3 degrees, and we can have a big conversation about different values for ECS. If we now overlay our high and what we're calling intermediate, what we find is that, yeah, okay, there's a whole lot of spread according to the spread in our assumptions of URR, ultimately recoverable resource. But you could say, but there would be a spread associated with the intermediate line as well. I've just taken the middle line. A realistic worst case scenario, in fact, is that global temperatures in 2100, which is here, will be a bit above the intermediate case and then stabilising. That's what that tells us. That is a highly controversial thing for me to say. If you want to come and talk to me about it, I'll be the guy sitting by themselves at lunch. So, what this is really saying is that those high emission scenarios, that RCP8.5 that we've heard so much about, really belongs over here in the hypothetical camp. And I've moved that up slightly, because we're slightly above low, that should read intermediate, obviously. This is the realistic worst case scenario. Now, this is an arbitrary delineation. If you want to start out at catastrophic and work up from there, you can. Okay? But the scenarios up in the top right corner should not be used. That is the conclusion of my talk. Thank you.